Good afternoon. It's my great pleasure to introduce today's colloquium speaker, Professor Fabio Finelli from INAF, Italy, one of the top labs and institutions of Italy, which does physics. And he is at Bologna. So Fabio has been a cosmologist focused on the early universe and also how to understand it using observations. So he was essentially leading the Planck efforts on the inflation, how much of can infer about inflation from the Planck data. And he has been a key member of the Planck collaboration. Currently, he's also a member of Euclid, which is a major survey done by a space mission, and Lightbird, which is a Japanese European satellite that would, space mission for CMB that is being, that is getting ready, and the Theseus collaboration. He's, of course, co-authored many, many papers, over 300 papers, 30 postdocs, PhDs, and master student. So he will be giving us an idea of the observational status of cosmic inflation. So as many of you know, that's one of the paradigms under which we think of the current universe. And no better person than Fabio, who's been working with the latest data from Planck, to speak about it. Thank you, Fabio.
Okay. Thanks a lot, Tarun, for the introduction and the nice invitation. It's my first time here in Bangalore. And I'm here also within an Indo-Italian research mobility program financed by the government of India and Italy, and is co-led from the Indian side from Professor Asra at the Institute of Mathematical Science in Chennai, Tarun here in Bangalore, and Professor Sriram Kumar from IIT Madras in Chennai. So I'm going to talk about the observational status of inflation and perspective of for future observation. We'll take a journey through the almost 14 billion year history of the universe, which is drawn here in an artistic view. So we give a summary and of this of inflation, which was the era of accelerated expansion that the universe underwent when it was a tiny fraction of second old. So this was a quantum and cold stage, followed by the formation of matter in a high temperature plasma, in which it was tightly coupled to light. Then, due to the expansion of the universe and its consequent cooling, light and matter decoupled, and the cosmic background radiation came to us, giving a pristine snapshot of the universe when it was 380,000 years old. So the standard Big Bang cosmology based on Einstein equation, the assumption of homogeneity and isotropy, and the matter described a perfect fluid has been supported by key measurement of the 20th century, such as expansion of the universe, nucleosynthesis of light elements, and the existing of CMB radiation. However, it's incomplete because of many puzzles, among which the flatness problem, the monopole problem, which the standard Big Bang cosmology cannot give an answer for. So cosmic inflation is the minimal early universe framework which addresses this puzzle by postulating a nearly exponential expansion before the thermal era. So if this expansion would be driven by a cosmological constant, it would be exactly exponential, but it would never end. So the simplest model involves a scalar field, a real single field scalar field, which in in some particular kinematic condition, when the potential energy dominates over the kinetic energy, which is called a slow roll regime, leads to a nearly exponential expansion that will end during the coherent oscillation regime of the inflaton at the bottom of the potential, where the inflaton it is supposed to decay in additional particle and re-heat the universe in a hot state. So in this way, we have a causal explanation of the initial fluctuation that we observe in CMB and large-scale structure. So in this plot, we have the logarithm of physical wavelength versus the number of V-folds, the logarithm of the scale factor which stretches the spatial section. And there is this h, which is the inverse of the Hubble parameter, which is the derivative of the logarithm of the scale factor, which in a standard Big Bang scenario would be the scale of causally connected patch. So in this case, is not the scale of causally connected patch during inflation, and you have sub-Hubble scales which are now stretched by the exponential expansion to observational, to scale which are relevant for observational, and they acquire a final spectrum on long wavelength from initial quantum fluctuation, which is nearly scale invariant. So we have a joint mechanism, a unified generation mechanism for nearly scale invariant spectrum, both for tensor perturbation, which are gravitational waves, and scalar perturbation, which are the density perturbation coupled to longitudinal pressure. And here there are some details of this power spectrum, which are nearly power law. And we have that their amplitude and their spectral indices are connected to the physics of the inflation and to the derivative of the inflationary potential for the simple models in which the kinetic term is a standard Klein-Gordon term. So in addition to a power law, there are slight deviations called running of the spectral indices, which are predicted in the simplest model as quadratic in this parameter epsilon, which are called slow roll parameter and are supposed to be small. So this additional scale dependence encoded in the running should be small compared to the spectral indices in tensor and scalar perturbation. So in addition, for the simplest model, you have a prediction for the tensor to scalar ratio R, which is the ratio of the amplitude of tensor over scalar at a certain scale, which is locked to the tensor spectral index to the lowest order. So this is an important assumption which is used in data analysis for the simplest models. There are predictions also for higher order statistics. So we have the so-called B-spectrum, which is the 3-point function for curvature perturbation. And in this case, the non-Gaussianity prediction are very small, below the detection threshold for experiment. And this is true for the simplest model, but then there are models which more complicate as non-canonical kinetic term, which predicts instead non-Gaussianity, which could be detected. And the same happens for multi-field inflation, which have an FNL, which can be of the order 1 and therefore detectable. Okay, so in summarizing the observational status of inflation, CMB has currently the lion's share of the constraining power due to the amazing progress in measuring anisotropy in the last 30 years. So CMB probes a regime for linear perturbation in which perturbations um, are small and much simply model with respect to the power spectrum of matter, which can be compared with galaxy statistics and other large-scale structure tracers. So the formation of CMB anisotropies in temperature and polarization. This is a rendering of maps from the latest Planck release in 2018. We have temperature and polarization in the Stokes parameters, Q and U. Actually, the polarization is better described in turning in E and B parameters, similar to what we do with electromagnetism, which exhibit more definite parity transformation. E is parity even and B is parity odd. And from the different type of dependence on the multiples, the signature of scalar and tensor perturbation can be distinguished, since they have a very different imprints in multiples, in temperature, which is in black, in E-mode polarization, which is in red, and in temperature E-mode polarization, which is in green. So B-mode polarization, primordial B-mode polarization, is instead a characteristic imprint of gravitational waves, in particular from inflation, and this is why it is called the smoking gun of inflation, the search for primordial B-mode polarization. So this is what, in an historical perspective, how the three generations of satellite, COBE, WMAP, and Planck, have measured anisotropies at smaller and smaller resolution with higher sensitivity. This is just to give an idea of the map, and this is how the characterization of the temperature power spectrum has changed in approximately 20 years, right? From 98, in which we had the first measurement by COBE at low multiples and a compilation of suborbital experiments, to the temperature power spectrum measured by Planck with below the residuals with respect to the best fit theoretical model of lambda CDM. And as I said, it's not just temperature, but also E-mode polarization, TE cross-correlation, and also the measurement of lensing, the field which characterized the deflection of photons in their way from the last scattering surface to us. They are deflecting from structure formation. Planck made a measurement from a conservative measurement from 8 to 400, and has shown how this additional likelihood it's worth to be inserted with the temperature and polarization likelihood. So just to fix, for those who are not in cosmology, just to fix some of the parameters which enter in the discussion. So the lambda CDM is the model with 6 parameters which best fits the, which provides a sufficient fit to Planck data. It's characterized by a flat geometry of the spatial section, baryon and cold dark matter density, a proxy parameter to H0, which is theta MC, the Thomson scattering optical depth to reionization, tau, and the 2 parameters which characterize the amplitude and spectrum of scalar perturbation, AS and NS. So Planck, with the temperature polarization and lensing has reached a precision of percent level in these parameters, except for tau, for the understanding of reionization, which is at the level of 10%. And just again, for an historical perspective, these are the evolution of the uncertainty in some of these parameters from pre-WMAP era to the release of Planck data. So I'm concentrating on this release that I've been working more on Planck, the so-called DR3. I mean, this was a nearly final attempt for the Planck collaboration. There has been new maps called DR4, which is a new pipeline in which LFI and HFI are jointly analyzed. There have been also attempts to combine, well, not attempts, a big program to combine WMAP and Planck LFI maps in the Beyond Planck program. There have been new analysis at low L and high L in terms of likelihoods. There is a very important update of the Planck lensing likelihood in N-pipe DR4. And however, the changes in lambda CDM parameter are within 1 sigma by this update. So this is just to state that what I'm going to say is not, it can be updated, of course, but is still a consistent picture, and also demonstrate how the CMB science is in a mature stage in which different data treated by different pipeline lead to consistent scientific results. And indeed, I mean, there is a lot of going on in CMB experiment, either at higher resolution, higher than Planck, or better sensitivity, or together. And this gives the idea of how this measurement, beyond those in blue, which are Planck, are quite consistent with a lambda CDM cosmology, which is here shown by the best fit as black lines. This was for temperature and polarization, and this is for lensing. This is a more recent figure from what we call ACT DR6, Atacama Cosmology Telescope, which released the lensing data in 2023, again with a broad consistency with previous result. And this is the scorecard, the Planck scorecard of inflation. There is a concordance of this result with the key prediction of the simplest inflationary model. We have a nearly flat universe by Planck alone, by Planck data alone, which can be reinforced by combining with baryonic acoustic oscillation. We have 8 sigma detection of NS, different from 1, different from exascale invariance. We have no statistical evidence of a running for the scalar spectral index. We have a measurement consistent with 0. We have the main non-Gaussianity shapes, which have been measured again consistently with 0. We have discussed only curvature perturbation, but in case inflation is driven by more than one field, there is the chance that initial conditions are not fully characterized by curvature perturbation, but there could be also isocurvature initial condition eventually correlate with curvature perturbation. Again, a very dedicated analysis to this problem carried by Jussi Valivita and collaborator show that the amplitude of this curvature perturbation are very tight constrained. And we have no signs of strings and other topological defects. So this is instead the page connected to the tensor to scalar ratio. We have an upper limit from Planck data alone, which is further constrained by the bicep, Keck array, Planck, WMAP likelihood, a B-mode polarization likelihood, which lead to tight constraint in 2018, about 0.056. With the subsequent release of bicep and Keck data, this constraint can be even tighter to the 3% level. And this leads to a constraint on the energy scale of inflation or to the Hubble parameter during inflation, which is an energy scale which is in the ballpark of 10^16 JeV or 10⁻⁵ for the Hubble parameter. So since simple models are consistent with observation, this is the plot, the money plot for this type of science of NS versus the tensor to scalar ratio, where you have the 68 and 95% confidence level of Planck alone, Planck plus bicep, or Planck plus bicep and baryonic acoustic oscillations. This is an analysis where we fix NT to R as predicted in the simplest model, and there are some lines as the convex concave line, which shows that in particular bicep Keck likelihood push the prediction, the constraint on R in a way that concave potential are completely allowed. And on top of this, there are some also prediction of a selection of renowned inflationary models with associate the uncertainty due to the heating stage model as between 50 and 60 folds to the end of inflation. So we have natural inflation. In purple, we have the monomial models, which in case of a quartic and quadratic potential have been ruled out during the Planck release. And there is the Starobinsky model, with the first model proposed, which predicts NS in the correct ballpark of 0.96, and the R, which is at the level of 4 in 10⁻⁻3. So it's completely consistent with the data. If you now fold in the most recent constraint from bicep and Keck array, you have a tighter constraint on R, and you have that many of these conclusions are tightened, okay, in terms of rejecting, for instance, monomial potential and preferring concave potential. This analysis highlights the importance of the simplest model, NT equal to minus R divided 8, but what happens when this condition is relaxed, okay? We want to analyze data without this theoretical prior. This analysis is strongly supported by many theoretical models which predict deviation as Dirac-Born Infeld inflation or Galilean-like action or non-abelian gauge inflation. So eventually a sign of multi-file dynamics. So what we wanted to ask was what is the importance of this prior in that analysis? This was an important question at the time of bicep 2. which anyway, with the advent of reliable B-mode polarization likelihood, this we see that goes away. It's important to note also that we avoid the use of using R and then T, because the constraint on R would be dependent on the theoretical, on the priors for NT, and therefore we use a two-scale analysis. We promote the tensor to scalar ratio at a certain pivot scale to two tensor to scalar ratio at different scales. This leads just with the update with the bicep cake likelihood 18. This leads to these results by picking up two different scales for the two tensor to scalar ratio. You see how it improves due to the update in the bicep cake likelihood, solid line versus dotted lines. And then one can also see how the prior of slow roll of simplest model perfectly fits in the, is perfectly consistent, do not lead to bias results. And this allows also to fold in the information from small-scale experiments, from the upper bound of LIGO in Virgo, which induce a change in the posterior, eliminate all the blue spectral index, which would lead to a relevant signal at LIGO Virgo scales. So we have discussed this extension of the simplest inflationary model. Let's see another extension. In the audience there are Tarun, Rajiv, who have worked hardly on this. The outliers in the power spectrum from the lambda CDM best fit. I mean, do these are just random fluctuation, or they bring some new physics in by fitting better this oscillation, in particular in the temperature power spectrum, which were seen also in WMAP. So they could be connected also to some issue in Planck data through the various release. There was this excess of smoothing in the acoustic peaks, which lead to an AL larger than 1, this phenomenological parameter which characterize the lensing in the temperature and polarization power spectrum. And from the theoretical point of view, this could be connected to departure from the slow roll paradigm. So we search for this feature in different ways. First, in a template-based approach, we consider templates which are characterized by oscillation around a certain scale. On the left, these local features, or global oscillatory feature which have oscillation through the whole range of wavelengths probed by Planck. So we show, either with a Bayesian and a frequentist approach, that we have an improvement in the fit of the order of 10 by this model with respect to the lambda CDM, but because of the additional parameter, these do not lead to models which are favored with respect to the simplest power law model for curvature perturbation. And these are, for instance, two figures which I think are in the legacy of Planck, which show how the amplitude versus frequency for logarithmic and linearly spaced oscillation are constrained by Planck data. So with an amplitude at the level of few percent at most. So this result, based on a template approach, being corroborated and confer by 3 independent primordial power spectrum reconstruction, which do not use templates. I'm showing just the Bayesian reconstruction, which makes a knotted power spectrum and show that any additional knot beyond power law, which is n equal 2, are not preferred. And I must say that this reconstruction were really prompted by an important paper by Diraj and Tarun and on Planck DR1 data, which really prompt the collaboration to look into detail to blind the reconstruction with all the available likelihood. So this was the result of on Planck DR1 data on temperature. Okay, so let me go now to the future, which part of it is already ongoing. I mean, there is a lot of offers from ground with many experiments and also suborbital experiments and space concept, right? The most advanced one is Lightbird, which has been down selected by ISES and is the highest priority for the Japanese space agencies. But then there are other important concepts as CMB Bharat or PIXI or PICO on the US front. Okay, so the scientific program of this experiment has been properly spelled in many white papers and many programs of the projects. Indeed, concerning temperature and the mode polarization, there is some discovery opportunities. The number of modes in polarization are definitely many more to be discovered. The blue line with respect to the red line, which is basically Planck, in polarization with respect to temperature. And the main driver is obviously the search of B-mode polarization from inflationary gravitational waves. This is a compilation which shows all the upper limits for this type of polarization and the implication that we have been showing from current data. So how this plot evolve for this future experiment. I take the example of Lightbird, which is mainly driven by a scientific requirement of having a sigma r at the level of 10 at minus 3, which would allow a detection of the Starobinsky model, which is the model which is among the preferred one from current data, or eventually it would lead to a upper limit in case the scale of inflation is low and do not produce a tensor to scalar ratio which can be detected, and this would lead to an important upper limit for concave model with a scale at the level of the Planck mass. And in case you'd like to abandon NT equal minus R8, the discovery potential is not just roughly an order of magnitude with respect to current limits on R, but it would go to around 2 orders of magnitude. This is the prospect to constrain the 2 scales when we do not impose the prior on NT of the simplest model. Sorry. Okay, and what about instead polarization at high multiples? So, as I was saying, the future is now. In this case, we know that the sharpness of the transfer function in polarization would benefit, in particular, at high multiples in order to probe features, because of the theoretical prediction. And this is an example for South Pole Telescope 3G 2018 data, which show how in polarization the SPT data are much more, have much smaller uncertainty with respect to Planck and go to IRL. So this lead eventually to a combination for the parameters of the lambda CDM to an improvement of 10%, but it can be larger in extension of this, like for instance for features. I mean, this again is a larger, is a graph which show again the comparison of Planck SPT3 data and their consistency. And so we conservatively combine this data and test for simple models of oscillations, two with constant amplitude and two with a Gaussian envelope. So it's interesting that the combination of Planck and SPT3 data, 3G data constrain much tighter, in a much tighter way, the amplitude for linear and logarithmic oscillation, while instead for Gaussian envelopes with smooth oscillation, then this amplitude is not sensibly decreased. Okay, let me now go to large-scale structure, since this is the large-scale structure decade in which many galaxies are in operation or in preparation will bring stage 4 sensitivity and will measure to unprecedented precision the statistic of galaxies and other matter tracers. So even if dark energy, dark matter were the main scientific driver for these experiments, we expect constraints on the initial condition quite competitive with those from CMB. Because either they will extend the level arm towards higher K, or they will provide an independent measurement at the same scale of CMB. So we had the DAISY data coming out this year. First, in April, the baryonic acoustic oscillation in 7 redshift beam from 0.1 to 4.1. We had 2-point clustering measurement a month ago. And we have also images from Euclid, ESA medium mission with contribution from NASA, launched in July 1st of last year. We had fantastic images like the Orsed head last year, or early release observation that were released in spring this year. This is an image to the right top of an Abel 2764 cluster. And in particular, Euclid, because as is on board either a photometric and a spectroscopic instrument, will provide a combination of what we call now the 3 2-point statistics, like we had from the dark energy survey or from KITS, and the spectroscopic and the galaxy clustering in Fourier space from the spectroscopic survey. And it's interesting that these two measurements could eliminate degeneracies, which could be present in either of these two measurements taken separate. As we see here, sigma 8 versus NS, we see that the purple galaxy clustering and the weak lensing are kind of orthogonal, and the resulting constraints are much tighter due to the combination of these two instruments. And we shoot basically a release in 2026 as data release 1. So in the years, we study in detail what this galaxy survey can bring, again, for features. This can be imprinted not only in the CMB, but also in the matter power spectrum. The analysis on linear scales might be simple, but in order to exploit the whole information from galaxy surveys, it's important to extend to non-linear scale. So we use embodied simulation to basically inject this superimposed oscillation as initial condition in this simulation. And what we saw is that the gravitational instability at non-linear scales damp this oscillation on non-linear scales, damps the coherence of this oscillation. And this is important to be taken into account when you analyze data in which you try to recover the matter power spectrum at Z1, 2. So we studied this, we approached this also in a semi-analytical way, and we insert it in data analysis of real data and forecast in order to show that galaxy surveys could provide constraints which are of similar capability with respect to CMB. Okay, let me conclude with just the last topic, stressing that we have studied it in detail, basically by CMB large-scale structure, approximately 4 decades in wavelength. Maybe this can be extended with 21 centimeters to smaller scales, but there are observations which can complement to smaller scales this CMB and large-scale structure constraint. In particular, spectral distortion, this has entered in the scientific program of concept for spectral distortion measurement beyond COBE-FIRAS of 1992, and which I've learned today have been pursued by many RRI colleagues. So this is an example of how future CMB concept for spectral distortion could probe the power spectrum at scale much smaller than the CMB and large-scale structure. And what we have used from a theoretical point of view, and to design models which have prediction and bumps on small scales. So with the same theoretical equipment of producing feature at CMB and large-scale structure scales, one can study models which produce large bumps in scalar perturbation at much smaller scale. An important difference is now these bumps can have a much larger amplitude that they can induce additional gravitational waves, secondary gravitational waves, which could be detected by PTA, SKA, or LIGO, Virgo, CAGRA, or LISA. So we studied this in a class of model in which the kinetic terms are coupled, and we studied this phenomenon of 2 stages of inflation also in the hybrid inflationary models which are consistent with the CMB large-scale structure. And the twist we gave to this study more recently in a paper led by Matteo Tagliazucchi was to use this these models which produce large bump in scalar perturbation, which could be an explanation of the pulsar time array measurements, okay? indeed, we have this hint of a stochastic background of gravitational waves by different timing array, pulse timing array experiments. So we use, and this is a type of physics that to which has been paid a lot of attention also by the pulsar timing array experiments. So basically we pick up best fits or models which nearly fit the pulsar timing array experiments, and we show how Pixie, a concept like Pixie, could be important to probe these models. So if you have a model which aims in fitting the pulsar time array as secondary gravitational waves, some of these models have a signal also in the Pixie window function. So this could be an additional science case for a Pixie experiment. So let me close here with the conclusion. So the CMB anisotropy pattern is currently the most decisive data set for inflation and its measurement, are consistent with the key prediction of the simplest inflationary models. There has been a lot of search for departure from the simplest model, and I've just presented how these departures are tightly constrained by temperature and polarization data. So the search for models which fit better the anomalies in the power spectrum or beyond 2-point statistics are not preferred over the lambda CDM model, either because of cosmic variance or the sensitivity of current experiments. However, forthcoming E-mode data will be important, and also B-mode polarization data will have the promise to constrain the scale of inflation to scales inaccessible from the laboratory. We are in the decade of galaxy surveys, so we will have data which from galaxies which lead to constraint comparable to the CMB ones. And I've closed with a remark on CMB spectral distortion and their synergy with new observation like pulsar timing array and other constraints from LIGO, Virgo, and Kagre detection, direct detection experiment. Okay, thanks a lot.
Thanks, Fabio, for such a great talk. We're open to questions now.
Very nice review of various aspects of inflationary cosmology, Fabio. A couple of questions. On one slide, you were mentioning these constraints on different shapes of FNL. So a quick look tells me that everything is consistent with a single field slow roll model, in fact, with the canonical structure of the Lagrangian. But if you carefully look at the FNL orthogonal, this is not consistent with 0, even with 1 sigma error bars. Error bars are large, but it's still not consistent with 0.
Yeah.
So is there already some, if you take them as sort of face value, is there already some indication here? Yeah.
Yeah.
So the last one is not consistent with 0.
Mm-hmm.
So is there already some indication, if you just take these numbers, about inflation being beyond having canonical structure in terms of action? Can one infer something from here already? And at the same time, the second part of the question is that, to what extent these constraints or these errors are supposed to be reduced in future with depolarization measurements?
Yes, this is a very good question. Thanks. So for the orthogonal, this is a bit more than 1 sigma. I wouldn't consider, I mean, I would keep a look at it, but I would not take as a measurement.
Okay.
Yes, it's 68%. Even if their upper limit, I'm quoting the 68% confidence level. So basically, 2 sigma will be an upper limit.
Okay.
From the point of view of CMB, we have very interesting forecast, right? This depends on a combination of sensitivity and angular resolution. So I think that in the white paper, in the program, you will find how CMB can improve these limits. It's not directly a question, but let me say that in the middle there are large-scale structure. So for the local one, this we expect interesting limit, competitive with the current CMB. And actually, I mean, I'm more involved in this since I have a colleague working on this. There is all this branch of analysis which goes beyond summary statistics, like field inference, and that leads to even tighter constraints on non-Gaussianities.
Okay.
So there are nice prospects, at least for the local. I don't know if the orthogonal and equilateral can be improved significantly.
There are no questions I have. Okay. And a few slides later, you were showing these constraints on R and NS using the LIGO-Virgo, including the LIGO-Virgo data sets.
The upper limit.
Yeah, upper limit. So I wanted to understand what information from the LIGO-Virgo observations is being used to in the analysis.
Yes.
Here.
So this is a very simple argument extrapolating the power law spectrum
All the way to LIGO-Virgo.
all the way to LIGO-Virgo frequency with the transfer function.
I see.
And it can be furtherly refined, for instance, take into account the running, which is important. Then one would have maybe a different type of results. So this was just a power law. But LIGO-Virgo should fall within the standard paradigm of 50, 60 folds.
Okay, okay.
So this basically leads to a change in the posterior. Obviously, you could have a model with a very small r, which is still consistent with LIGO-Virgo. There is obviously the nucleosynthesis limit on R, but is a change in the posterior, let's say. One can use a similar argument also for PTA, for instance, which is at much larger frequency with respect to LIGO-Virgo. But that's a detection, so this would lead to a completely different phenomenology.
Yes. And perhaps one quick, so what is the current status of PIXI?
Well, I'm not completely updated on that part. PIXI has been submitted various times to NASA. I'm more updated on the attempt on the European side. So there is an effort also from the European side to propose a spectral distortion space satellite. And actually, in what has been called Voyage 2050, I mean, there was a recommendation from the senior panel on spectral distortion / gravitational waves for a space mission. But we are talking about 50s, 40, 50s.
Few more decades.
It could be also such a complex experiment which might not fit in a M mission and would need a cap of a L mission. So it seems something for the next generation of the space concept. I learned here that there are several attempts to measure the spectrum at different frequency from ground or nice idea from space.
Thanks, Fabio.
Any further questions? Yes.
Thanks for presentation. Very interesting. I learned something new. But my question probably will sound somehow stupid. It concerns the following thing. Baryons, parameters of baryons in the universe, they have uncertainty around 10%. And the baryons are actually all observations most of observations come from baryons. How this uncertainty in baryons, 10%, propagates to determination of the spectral index, I mean the power index N, because 10% here and the power spectrum is somehow in the second side, around 1%. You showed this. Thank you.
So may I ask you, this 10% in baryons, are you referring to some astrophysical measurements?
Yes, these astrophysical measurements, and they show around 10%. And moreover, quite recently, it seems with James Webb, it seems that the structure in the Uranus starts very early, say up to redshift at least 10, 14, 16 even. So, and some perturbation of the forming structure can bring some distortion, right?
Yes, I mean, this, I presented, let's say, CMB only constraint. I focus on CMB only constraints. The consistency with other observation as JWST was absolutely not covered, is at the forefront of research. It's very interesting. It is an evolving field. It's unclear if it has to do with galaxy evolution only, or there is some need of change in the primordial power spectrum. Is definitely something to look at.
So in the light of, for the whole approach to look for unmodeled deviations in the power spectrum, so the approaches here, I mean, with even knots and, smooth curves through it, that's not as general as, because once you say I don't have a power law power spectrum, it could be anything. So I would like to know your views about the whole program that you're pursuing on deconvolving the power spectrum at every data point, I mean, which is what Arman and then later Dheeraj and Arman were doing.
No, this is very interesting. I try to give credit
Right.
to this analysis, which prompt different analysis within the Planck collaboration. I think that I mean, the complementarity of different approach should be really pursued ahead. So.
Yeah, no, I agree, but I mean, I'm saying that, what would be, once you say no power law, not power law, then, it just opens a whole, possibilities. So the question is, you can do soft deviations, you can do, but then there's a basis in which you can do, kind of wavelets and things like that, all kinds of things. So in that context, I see that not too much has been explored, right? I mean, this was this knots and then,
There was knots, there was the penalty likelihood by Martin and Chris. I'm talking about the Planck paper.
Planck, yeah.
And I know very well that there is the Richardson Lucy that Arma, you, and Andy Raj
Right.
is bringing ahead. And actually, it was very important also to give an interpretation of the AL problem,
Mhm.
which I didn't touch here.
Right.
Um,
Thanks. I
okay.
just wanted your views.
Any further questions? If not, then let's thank our speaker once again
Thank you.
for the talk and the question and answer. And now I invite Tarun to present souvenir to our speaker.
Just a little memento from
Oh, okay.
Raman Research Institute for the colloquium. Thank you so much.
Okay. Thank you.
This is a Nature India volume on the science that has come out, highlights of science that has come out over the 75 years.
Okay.
Some selected highlights. And,
Okay.
from
Thank
our-
you so
from
much.
Research
It's an
Institute.
honor. Thank you.
If you like this pictorial biography of Raman.
Yes.
it's
Thank you so much, Tarun.
Oh,
and-
okay.
Okay.
He wants
Yep.
to take-
Okay. Thank you.
Okay, great.
Thank you.
Thanks a lot.
So thanks once again, and please join us for tea and coffee just outside the auditorium. Thank you.
Oh, thanks. Thanks. It was completely unexpected. Thank you for this.